there. Okay, so first problem, a couple things to consider. We got Hooke's law to deal with. Oh gosh, nothing is going right. Stan, keep a close eye on me, please. Okay, there we have a pen now. Okay, so formulas like this, I'll give them to you on, like last time you had the cheat sheet of all those derivative formulas you could use to come up with antiderivatives. This time I'll give you that plus a bunch of physics problems, that formulas that I think are relevant. So for example, I don't need you to memorize Hooke's law. I'll just restate it, but most of you probably have it memorized. It says the force is proportional to the distance when you stretch or compress a spring. So we've got that going on. One thing, a lot of times we're in the habit of just grabbing numbers and throwing them in somewhere. And so the other day when I was on a roll with these problems, I took the 1900 and plugged it into the force. What's wrong with that? It's work, not force. Yeah. So I can't just apply Hooke's law directly here because that 1900 is work. So just a note about work. And another thing you got to be careful of in the online homework and in the book, they use W for weight and they use W for work. Work and weight are not the same thing, so be very careful about the W's floating around. Work is equal to some force over the distance that force is applied. If the force is variable, then you have to use integration to come up with it. And what we're told here is that the work done is the 1900 joules. So in order to find the constant there, I have to work with Hooke's law. Now, the error I made in class the other day is when I was applying this to the integral, the dx is our distance. Little chunks of distance. I threw an extra x in there by mistake. I don't know why I did that. And I remember looking at it, I'm like, man, the units don't work here. And one thing I usually do when I'm playing with physics problem is I double check the units to make sure things are lining up. So just to double check this here, what's force usually measured in for metric system? Newtons, and this is something I can give you on the test too, a cheat sheet of those measurements. Newtons, and newtons is kilograms times meters per second squared, if we happen to need that. A joule, on the other hand, is a Newton meter. And so what I'm taking here is dx is a variable. It is a distance, right? It's not just something sitting at the end of the problem we can ignore. It's quite relevant. So that right there is meters. What's force measured in here? Newtons. So this integral does do Newton meters. And so yesterday in class, I threw an extra x in there, which gave me Newton meters, which I have no idea what that is. Maybe Mr. Schmitz does or Mr. Oya does, but I don't remember ever seeing in physics a Newton meter squared. Oh, no, I can't think of a use for that. But maybe there is one. I don't know. All right, so this is the integral I need. So for our problem here, it does sound familiar in physics? I don't know. I'll stop by and get his critique on these problems that he doesn't like. What's that? Pressure is force per unit area. So that would be something like Newtons over meters squared. Yeah, so like literally like me pushing on you. Yeah, if I push the same force with my finger, that will hurt versus the same force with my fist won't hurt as much. Okay, so for us then what we have is the integral of kx dx. We don't know k yet. But this integral, once I have an antiderivative and some boundaries, has to be equal to the 1900. Okay, so the next question is, what are the boundaries here? So here it says it takes 1900 joules of work is key there, to stretch the string from its natural length 1 meter. So if the spring is just sitting and no one's messing with it, it's 1 meter long. Then we stretch it to 5 meters. So what are my bounds for the integral here? Okay, 1 to 5 was my first guess too, but that is incorrect. It's 0 to 4. Yeah, it's the displacement that's important. what changed? It's naturally at 1. That's its normal base state. We stretched it to 5, so it actually moved from 0 to 4. And that's the other trick here. So x is going from 0 to 4. And so what we need to do for this problem then is we need to come up with an antiderivative and then set it equal to 1900 and solve for k. So let's just do that quick and give us an easy warm up. I'm getting 8k when I clean that up. Anyone else get that? Got a couple nods. And I think what it was equal to, is it 1900? Yeah. So then k must be 1900 over 8. There we go. So let's see, if I cut 1900 in half. Oh, you already got an answer? 475 halves. Okay. So that should be the spring's constants, which is, I think, what we were looking for here. So the tricks on this one, recognizing that the 1900 was work, not force, and then the actual displacement was from 0 to 4 because it was naturally at 1, nothing applied. Okay. So those are the two tricky parts on that one. All right, let's see if we can get a good job out of the computer. 475 over 2. All right. Okay, so next I need to go over the pressure problem that I messed up, which I think was problem number 12. Yeah, so we're going to redo this one right here. So let me get numbers, and this is water, right? Yeah. And can I blow that font up? Yes, it's got some weird things just because the way things are built on the web. Let's blow that up to 24. That's better. And get rid of the extra, the only extra stuff. Yeah, I think so. Okay, so here's our problem. What else do we need? Okay, so we also need this picture. And it will not let me grab the picture, really? Fine, we'll get it the other way. Oops. Okay, so here's our picture of the trough. So the thing about pressure is it doesn't matter how big the pool or tank is that way. What matters is the cross-sectional area and the depth of it. Okay, so we have this triangular plate to consider. And what do we know about it? Let's see, it's 6 feet wide across the top. So, and let's see, they're recommending putting the x-axis down here and the y-axis right there. Now, most people aren't very good at making 3D pictures, which is fine. You should always do a 2D sketch of the plane that you're working in with cross sections. That's a good idea. So this is the point 0, 0, right? And this would be the point, let's see, 3, 14. It's 14 units up and total of 6 across the top. Other thing to consider here, I'm going to have a rectangular chunk of area across that way, which means I need things in terms of y. So this line coming through here, I would like to write it as x equals. So if it's x equals instead of y equals, we flip the slope. So instead of 14/3, it's 3/14. So keep in mind what we just found right there is that horizontal distance there. So for this piece of area here, we need to double that. So a chunk of area for us here that we're examining the pressure of is going to be 2 times that. And then it's got a height of dy. So cleaning that up, chunk of area is 3/7 y dy. All right, let's see. What other information do I need to figure this out? Let's see, we had some physics formulas from the other day. What are the relevant formulas? So we need the weight of water, 62.4, yeah. So we're doing the fluid pressure stuff. So the pressure at a depth is just going to be the weight times the depth. And then the force is the pressure times the area. So altogether, what we need to consider is the weight density of water, the depth, and the area. So we need, for a chunk of force, the weight density of the liquid, the depth, and that area. So weight density of water is the 62.4. The depth is where I made the mistake the other day. So here, y is moving up. So y is the distance from here to here. That's not the depth. Depth is measured from the surface. I'm supposed to say surface, believe it or not, from the surface down. Okay. Now, if this tank were full, the top of the surface would be 14, right? But the question here is we don't know how many cubic feet are going to lead to that pound. So we have an unknown surface height, an unknown depth. So we're just going to call it D because we don't know what it is yet. So I'm just going to draw another red line here. That's just some number D. And this rectangle right here then is below D, right? D is above it. So my depth here is whatever the top is, D minus Y. Okay. So for my depth, I'm going to have a D minus Y. And then we already calculated the area. And every problem is a little bit different. With the conical thing, the cone we had the other day that we were playing with, the height that you pump stuff depends on your coordinate system. And in some problems, they had the point of the cone down here. In other problems, they put the top of the cone there and then went down. And that changes everything. So you always have to rethink, what are your heights? What are your depths? Every problem is different. Sometimes it's just straight Y. Sometimes it'll be something like 14 minus Y. Okay, it just depends on the way you set up the problem. Okay, so what else needs to go in here? We have our 3/7 times Y dy. And it's always a good idea to double check the units to see if things are working out. So what are we trying to calculate here? A force, right? So ultimately, this is some change in force. What's the 62.4 measured in? So I'm just going to pause to check units here. It is pounds per cubic feet. Yep. So that's pounds per foot cubed. And then the depth is measured in feet. And 3/7 y is measured in feet. Does dy have any measurements? Oops. No, dy, it doesn't ever disappear. It's always this little tiny quantity hanging out. What is that little tiny quantity measured in here? Yeah, it's feet according to my picture over here. Okay, so if I have pounds per cubic foot times feet times feet times feet, it equals pounds. So at least we have the right kinds of stuff in here. Okay, so we do have indeed a force. Hopefully it's the right force. Okay, and yesterday instead of a d minus y, I just threw a y in there. So that was my error. Okay, so now we need to integrate that through our boundaries. So we now have the integral of, I think I'll pull out the 62.4. And the 3/7 can come out too. Let's see, good. Move my integral. There we go. Times 3/7. And then let's see, what did we have in there left? We have a d minus y times y. And it's not a bad idea to distribute those. So that'll give me a dy minus a y squared dy. Did I catch everything there? Okay. Boundaries of integration here. Oops, wrong button. So let's see. The end plates, we're checking to see how much force they're going to get depending on what the depth we set, and we can't exceed 5,000. How many cubic feet can the tank hold? So we have a varying depth, right? We don't know what that is. Okay, the tank is going to start at 0 and go up to what then? D, yeah, whatever that varying depth is. We don't know what it is yet. No. And ultimately, we want that right there to be less than or equal to 5,000. But first, we have to figure that sucker out right there. Oh, gosh. I used D 2 different ways there. I guess I should have used a capital D, huh? That is confusing. No, it's not. I can't use a delta. That's illegal. I could get arrested by the math police there. Let's call it a capital D, maybe. Capital D. Where else does it appear? Capital D. Capital D. Yeah, it's not our derivative D, it's D for depth. My problem there, sorry. Okay, so this isn't too bad. We've got our 62.4 times 3/7. And then our antiderivative here is going to be what? Capital D y squared over 2 minus y cubed over 3 from 0 to capital D. And I don't know how much this is going to clean up. 62.4 times 3/7. The 0 is nice. So what do we get? We get d cubed over 2 minus d cubed over 3. And let's see, 1/2 minus 1/3 is 1/6. So in the end, we're going to get a 62.4 times 3/7 times 1/6 times d cubed, which cleans up a little bit. So we need to set that equal to 5,000 and then solve for d to come up with the proper depth so we don't exceed that 5,000. So whip out a calculator, see what you get. Grab Google as a calculator. So what do I get? I'm going to get 5,000 divided by 62.4 times 7 times 2. And then I want to raise that to the power 1/3. Ooh, that did not work out well. To the power parentheses 1/3. And Google tells me the depth is about 10.4-ish. Anyone else get that? So just double check, writing some things down. So I was considering the 3 goes into the 6 twice. 62.4 times, let's see, 3 is gone, so I don't have times anything. Over 2 times 7 is 14. D cubed equals 5,000. So D cubed equals 5,000 times 14 over 62.4. And then we want the cubed root of that, or the power 1/3. And so I get it's about 10.4, and that would be feet. Almost done. What was the question? Oops. Question was, I think you had to find the volume. All right, how many cubic feet can the tank hold? All right, so volume isn't too bad. We could do it with calculus or without. So one thing to consider, here's my triangle there. And let's see, something like that. And what do we know about this thing? How far deep was it? Anybody remember? 14 was the heights. It was 36 deep. Where's my picture? Okay, so it's 36 that way. If I can just figure out the area of that base there, then I'll have area of the base times the length there will give me the volume. So that triangle right there, we know that the distance from here, actually the distance all the way across is, where'd it go? Right there, the 2 times 3/14 y. So that's going to be what, 3/7 times y. What's our y value here? That's the 10.4-ish number. I'm just going to call it D for a minute. Yeah. So we could call it D. So it's that distance across there is 3/7 y. What's the height of this triangle? Just y, right? So that means the area of this is 1/2 times 3/7 y times y, or y squared. If I multiply that by 36, then that right there has got to be the volume. All right, so I have the area of the base times the height. And we just need to plug in our 10.4 and come up with a number on that. So what do I get? If I go back to my Google calculator, I need to square this number. And then multiply by 3, divide by 7, multiply by 18, 832.9-ish. I got 85879. I should. Oh, does it? do not round until the final answer, then round down to the nearest cubic foot. Oh, because we don't want to overfill the tank, because then we risk busting the side. Yeah, good point. There's someone's thinking here. Yeah, the fine print. Yeah, it always gets me too. All right. I'm sorry. I owe you extra credit for that. So we would have to call it 832. Yeah, that's annoying. Okay, so those are the two problems I wanted to go over. What do you guys want to do? 11. All right. And then I'm going to give anyone that does the softball problem extra credit. And if you don't want to do it, then yeah, if you didn't, I'll look back at your grade. If you didn't do it, I'll just up your grade. If you did do it, I'll up your grade. So it involves change in kinetic energy, which I didn't want to go over, and I meant to delete the problem from the homework set. So, all right, what do we got? We have a semicircular plate, 13 inches in diameter, sticks straight down into fresh water with the diameter along the surface. Assume a force is exerted by water on one side of the plate and that the density of water is 62.4 cubic pounds per feet. So this is very similar to the problem we just did with the triangular plate. It's just a circular plate instead. So let's do it. And I think I might just try a screenshot this time. And I need all of that. It's always nice when they draw the picture for you. I especially enjoyed the milkshake problem. Did anyone do that one? The milkshake is, was it 6 maybe? No, it wasn't 6. Was it the one with the straw? Yeah, the one with the straw. Oh, it must be back further. Oh, there's 2 problems like that. Okay, so I will give extra credit for both the softball and the racquetball problem. Where did it go? Is it later on? It was like 10. Oh, it's like 10. And the thing that bugged me is their picture is totally not to scale. If you draw it to scale, then it actually looks like a milkshake container. Yeah, so their units are not proportional. Yeah, it looks more, like more like a martini glass or something. Yeah, that's kind of weird. Anyway, okay, let's do this problem. All right, let's set her up. What's that? Oh yeah, yeah, we got that. And yeah, and I meant, oops, wrong button. I meant to double check whether they gave us a ounces per cubic inch density. I wanted to convert that to compare it to like milk. All right, anyway, but I don't have that much free time currently. Ah, wrong button, darn it. Escape. Okay, so let's see, what do we have here? So they drew part of the picture for us. In this case, this is going to be my dy, that little height right there. Oops. Uh-oh, my pen's not tracking, hang on. If I can fix it. Okay, next thing we need to consider is the diameter is 13. Let's hope it's right this time. So that means out to the side here is going to be 6.5. And over here is going to be 6.5. And down here would be negative 6.5. So whenever you draw a picture, throw numbers in there so we know what we're looking at when we make calculations from that. Here the circle is centered at the origin. So that means the equation has got to be x squared plus y squared equals 6.5 squared. Which is another consequence of the Pythagorean theorem. Here we need x equals, so if we solve for x, we're going to get x squared equals 6.5 squared minus y squared. So x is plus or minus the square root of 6.5 squared minus y squared. Which do we want, the plus or the minus? Try again. If y is oriented up, we want the minus version of it. Oh, wait a minute. Sorry, I lied. X equals right side. Ah, yeah. Sorry, you're right. I have my boundaries backwards. So the plus would be this side. The minus would be that side. Yes, so Stanton is correct. We can go with the plus side. All right, so as far as the area of that plate right there, let's do that in red maybe. I need the distance all the way across, which should be what? No, just for this plate right here. If the plus represents the right side only, what's the distance all the way across? Twice that. Yeah, there you go. Okay. So it's 2 times that square root, 6.5 squared minus y squared dy. So there's the area of the plate. Next thing to consider is our force. And that's going to be the weight density of the liquid, which is water. So we got 62.4. This is going to be similar to last time. Times the depth. Okay, so let's see. Here is y equals 0, and here's y equals negative 6.5. So the depth is the distance from that line down. What will we call that? What is it? It's just y, right? Because doesn't y tell us where on the axis we are? And aren't we y below 0? Yeah, so in this case, the depth is just d. That's what I measured before. Every problem's different. It depends on where you put your coordinate system. You got to rethink. Oh, shit, what's the height here? What's the depth here? So I'm 99.7% sure that the depth is just y here. And then multiply by the area, 2 times the square root, 6.5 squared minus y squared dy. So then what we want to do is then integrate that. So what can we pull out? We can pull out the 2 times 62.4. So we might need it in terms of taking a derivative. Oh yeah, check that out. We're going to have a substitution. All right, let's leave it in. Good job, Stan. Nice eye. So 62.4 times the integral of 2y times the square root of 6.5 squared minus y squared dy. And although it's easy to forget that dy, it is an important unit that hangs out. It contributes to the units in the problem. All right, so question is, where are we integrating from and to? I think that'll work. Negative 6.5, almost, to 0. Yeah, because the plate is completely submerged with the top of the plate at the surface of the water. Yeah, so we're going to integrate that whole thing. Okay, so to come up with an antiderivative here, we're probably going to need to do a substitution on that. So let's give that a try. So we have the integral as y goes from negative 6.25, no, 6.5, sorry, to 0. 62.4 is hanging out, 2y is in there, square root 6.5 squared minus y squared dy. And what's a good candidate for a u? The inside of the square root. So if we let u equal the square root, no, sorry, no square root, just the inside, that would be trouble. 6.5 squared minus y squared, then du should be, oops, where's my u? Right there, negative 2y dy. And all we're missing is the negative. So that means the opposite of du should be 2y dy. So now, and let's see, what are our bounds of integration here? If we plug in negative 6.5 for y squared there, what's u going to be? 0. And if we plug 0 in, 6.5 squared. Yeah, so we could rewrite this as 62.4 times the integral as u goes from 0 to 6.5 squared. This right here is the opposite of my du, so I think maybe I'll throw a negative outside. And inside, I am just going to have the square root of u, du. That's u to the 1/2, right? We could rewrite it that way. It's a little messy still. So what's an antiderivative for u to the 1/2? It's going to be, yep, 2/3 u to the 3/2 as we go from 0 to 6.5 squared. I have everything in there. Negative 62.4, 2/3 u, yep. So I can pull out that negative 62.4. I'm still wondering if we're going to be off by a negative sign here. 2/3, and then we have 6.5 squared to the power 3/2. Yeah, I think our original boundaries were reversed. I think it should have been from 0 to negative 6.5, integrating from the surface down, because that's the way the depth runs. Yeah, it's you have to run the integral according to the depth. So the depth is 0 here and then increases that way, even though our coordinate system is positive up and negative down. So these boundaries were switched, which means these boundaries should be switched, which would get rid of our negative. So just ignore that negative. We have a mistake there. So this cleans up to be what, 6.5 cubed? All right, let's see what we get. Type that into a calculator. Calculator is here, clear. So 62.4 times 2/3 times 6.5 cubed. I get everything in there. 11,424.4 is the pressure exerted here. And if we double check our units, we should find that that's pounds. If the homework problem likes it, oops, wrong problem. Which one we were on, Stanton? 11. And it doesn't look like they changed the numbers on me. Woohoo, we did it. We got time to set up one more. What would you like to do? Homework, something from that sample test. I will post the solutions to that today. Nobody's got something they really want to do? No, it's a cone problem, spring problem. We did problems like that today and yesterday. Surface of revolution. Sure, because my claim is that there is an exact, which is rare among these kinds of problems. All right, let's give it a try. New page. So we're going to be able to set it up, not solve it in the last 5 minutes. At least I think it's unlikely we'll be able to solve it. Oops. New page. Okay, so a semicircle of radius 2 as the equation, y equals 4 minus x squared. That would be the upper portion of it. And we want to revolve it around the x-axis. And we want to then see what is the surface area generated. So there was a homework problem kind of like this one. So just quick sketch, always a good idea. So 1, 2, 1, 2. So my semicircle looks something like that. All right, so that is my y equals the square root of 4 minus x squared, and I want to revolve that around the x-axis, and we should, pretty sure, generate a ball of radius 2. And we're going to figure out how much paint it would take to cover that ball. Formula for such a thing is equal to the integral. Now, since we're rotating stuff, right, so imagine this thing is being rotated right there, we're going to end up with these circular disks. We're only interested in the edge. So there's going to be a 2 pi times the, that's going to be my radius there. That's just the y value. Times the square root of the Pythagorean theorem in calculus form, which is 1 plus, let's call it y prime squared. All with respect to y, x, sorry. Right, because that's a little chunk on the x-axis when I revolve around it in this way. Things to know here, well, this right here is my y. So I have to take its derivative, square it, add 1, see if that cleans up at all. So let's go for it. So step 1 is to find y prime. So we can calculate that sucker. Derivative of the square root is 1 over twice the root, if you look at it that way. Inside there is a 4 minus x squared. Chain rule applies here. Derivative of 4 minus x squared is a negative 2x. So that cleans up a little bit. That's negative x over the square root of 4 minus x squared. Step 2 is to square that sucker. And we can probably add 1 at the same time. You mind doing steps 2 and 3 together? So I think we'll have 1 plus the square of this, I believe, is going to be x squared over 4 minus x squared. That's nice, the square root went away. Common denominator is going to be the 4 minus x squared. So I think the 1's going to be a 4 minus x squared over 4 minus x squared. So my numerator is 4 minus x squared plus this guy here all over 4 minus x squared. We've almost got enough time to finish this sucker. That cleans up beautifully, right? It's just 4 over 4 minus x squared. So step 4 would be to take the square root of that. Oops. Which cleans up a little bit. I can rewrite that as 2 over the square root of 4 minus x squared. And then I can throw it back into the integral. So my integral is 2 pi times y, which is the square root of 4 minus x squared, times the little arc length chunk, 2 over the square root. Oh, look at that. Isn't that lovely? It's just going to disappear on us. So the square root of 4 minus x squared cancels itself out. Now we didn't set our bounds of integration. We probably should do that before I continue back. Let's see. X is pretty much going from -2 to 2, right? We're just zipping right across the axis there. So X is going from -2 to 2. We could use symmetry and double stuff, but I'm just gonna, oh yeah, let's use symmetry, right? That's gonna be way better because then we get to plug in 0. And I love that. Okay, so this is gonna be twice the integral as X goes from 0 to 2. Yeah, whenever you can get away with a 0. That cancels, so we just have a 4 pi inside dx. Finishing this up, we have a constant of 8 pi hanging out times x from 0 to 2. So altogether, what are we getting? 16 pi? Okay, well, we're a couple minutes over, so we better stop there. All right, I will post, I got another class right now, but right after I get out of that class, I will post my solutions in the same spot that sample test is. So just like over here, I'll put a little solutions there. Your test will be very much like this, but a little shorter in class, and you'll have a few problems to take home over the weekend. No, I wouldn't do that. You've already done the ridiculously hard ones for homework. Now you're just going to do moderately hard ones for the test. All right, that's it. Have a good day. Whoa, what happened there?